Hi everybody, welcome back to AP Statistics. This is Mr. Ropes, and today we're looking at the last section on linear regression for now. We'll come back to it when we do inference second semester. But for now, we're going to look at computer output, which is usually how it's displayed when we get our regression analysis, and working with regression models. So how do we use the line once we get it? All right, so here is an example of computer output. So we've got this scatter plot here. There is this line of best fit, our least squares regression line drawn in. We're comparing the miles driven versus a Ford F-150 resale price. So these are the prices in dollars that they've sold it for, and these are the number of miles it has driven prior to being sold as a used car. All right, so we're usually going to get a little mini tab. It's a stat program called minitab. It usually gives us an output that looks something like this. All right, so it says predictor over here, there's a constant, and then there's the miles driven. And if you remember, miles driven here is our explanatory variable, so that's our x. And then each of those has a coefficient. So that's the number that goes in front of x. So that means this guy right here, with that negative sign, is our slope. So that's going to be the slope of our regression line. This coefficient of the constant, it's kind of a weird way to say it, the constant coefficient. This is just your y-intercept. All right, these other numbers over here we're not really going to use for now. So this is the standard deviation in something. This is the standard deviation in something else, or technically standard error. These are t-scores. These are p-values. These will come back up when we do inference much later. These things over here, we probably won't ever use these. And here is the standard deviation of the residuals. So this comes up sometimes. So remember, the residual is how far each actual point is from the line. Like each of these distances I'm drawing in here would be a residual. Some of them would be positive, some of them would be negative. If we look at all those residuals and find their standard deviation, this is their standard deviation. So this is the average amount that the data points vary from the line. All right, so that's important. That comes up sometimes. All right, they usually give us r squared. So remember, that's our coefficient of determination. So that's r squared. If we want to get to r, we change it to a decimal. We take a square root. The r squared adjusted, we won't use in this class, but they always give it to us anyway. So don't worry about that. All right, so answering some questions here. What's r? What's the correlation coefficient? Well, if r squared is 66.4%, that would be 0.664. To get to r, we would have to take the square root. So we're just going to take the square root of that, and whatever that works out to will be our answer. And that works out to 0.8148, so maybe 815. All right, so it looks like that is a pretty strong correlation if we're at 0.8. And yeah, they do kind of line up in line-ish. All right, what's the equation for the line of best fit? So this is probably the most important thing from this is, can we get the equation? All right, so remember, we have two ways to write the equation. We can write it with y hat equals the intercept, the 38257. Actually, it's not plus, it's minus 0.16292. We don't always have to write all those decimal places times x, so we can write it like that. But if we write it like that, we have to define what y stands for and what x stands for, which is why it's often easier to write it with just the words in there. The predicted price is 38,257 minus 0.16292 times the miles driven. I do recommend doing it with the words in there. They like it that way on the AP exam. That's the way they write it in their answer keys, with the words in there. All right, so we've got a y-intercept, so that would be the price if there were no miles driven. All right, so if we're selling it used without driving any miles on it, it looks like $38,000. And it looks like we're going down a certain amount for each miles driven. All right, so here's examples. Most of these notes here are examples. The table below shows the output of a regression analysis of fat gain versus non-exercise activity, or NEA, non-exercise activity. Find the least squares regression line. All right, so how are we going to take these numbers here, however they are, and make them into a regression line? Right. If you need more time, stop it and think about it. But this right here, the coefficient of the constant, that's going to be our y-intercept. All right, so that's going to be like our a, if we're doing y hat equals a plus bx. All right, and NEA coefficient, so NEA, Non-exercise activity looks like that's going to be our variable. That's going to be our x. And so that means our slope right here is that. All right, and these are the only numbers we care about. The rest of these numbers are not important for making the line as far as we're concerned. So it looks like NEA is going to be our x, so that means fat gain is our y. And we need the 3.5, that's the y-intercept, the a right there. We've got a negative to that, that's our b, yep, and NEA is our x value, yep. So that was answer choice A. Next one, same information. Can we find our correlation coefficient from this information? Which reminds me, I think I made a mistake on the last one because I forgot about something. All right, so if we've got r squared equals 60.6%, that means r squared equals 0.606. So that means r equals the square root of 0.606. And if we take that on our calculator, we get 0.778. And now what I forgot last time, we have to look at our slope, and our slope is negative. That means r is going to be negative. So I forgot about that on the last time. I'll go back to that in a second. So if our slope's going down, that means r has to have the same sign. So r will also be negative. So there is our answer. All right, so if I go back to the first one here, oopsies, forgot, yeah. So r here was negative, look, our slope was negative, the line is going down, so we have to change this to a negative because it is also going down. So we have to get that from the table. We don't get that just from taking the square root. We have to look and see, what's the slope look like? Is it positive or negative? If it's negative, it needs that negative sign. If it's positive, we just leave it as positive. All right, so that one's right. We figured it out eventually. All right, so here's our regression line, which we wrote down before. Price hat, the predicted price equals the 38,257 minus the slope times the miles driven. So identify the slope and y-intercept of the regression line and interpret each. So the y-intercept is $38,257. Remember, that is our y value when the miles driven equals 0. All right, so this is, so the resale, so it is the resale value because we are looking at resale price, not new price, so it is still a resale. The resale price of an F-150 with 0 miles driven is predicted, there's a key word, predicted, to be $38,257. All right, so make sure we say predicted because that's what this line does. It predicts things. It's got a hat. It predicts. All right. And the slope, so here's our slope right here. So usually when we interpret our slope, the first thing we do is we say that our slope, S-L-O-P-E, equals negative 0.1629. We put it over 1. All right, and miles driven is our x, so miles, and this is dollars. All right, so now we take this and we write our sentence, and our sentence starts with, on average, for each increase in 1 mile driven, we predict a, let's see, it's negative, so it's decrease. I'm starting to say an increase. No, decrease in Ford F-150 resale value, or resale price, I guess, by this many dollars. 0.1629. If you just said 16 cents, that'd be fine too. All right, so for on average, for every increase or for each increase in 1 mile driven, we predict a decrease in F-150 resale price by 16 cents. There's our interpretation of slope. All right, now can we use our line to predict some stuff? All right, so use the regression line to predict the price of a Ford F-150 with 100,000 miles driven. All right, so 100,000 miles is within our range, like it's between 0 and like about 150, so it should work for that. Remember, it has to be in our domain here if we want to be able to predict it. It looks like it's somewhere between 20,000 and 25,000, but we can just plug in. So we can just take that 100,000 and just plug in for miles driven right there. There it is. And now we just work that out. And there is our predicted price. Right, $21,967. Yeah, that's definitely between 20 and 25. Looks like about 22. Yeah, that works. All right. And again, we didn't want to make predictions for like 200,000 miles driven because it's not on our chart. And we couldn't make predictions for negative miles driven, but I don't know how you get negative miles driven with a car. Lots of going backwards, I guess. All right, so more examples. A study recorded the number of cups of beer consumed and blood alcohol content, or BAC. Interpret the slope of the least squares regression line. So we got to be able to look at this and find the slope here somewhere and then say what it actually means. So take a second and do that. You may want to pause it. All right, so if we look at our predictor, we've got our constant. So that's our A, our y-intercept. So here's our x is beers. So that means our slope B is right there. So there's our slope. So that means we can cancel out the ones that don't have that number. And really, that's the only one that's left. So it's not that one. It's not that one. It's not that one. It's got to be the one that has the slope. So the sentence is, on average, all right, for each 1 beer increase, the predicted blood alcohol content increases by 0.321. So the sentence is slightly different here, but again, it's close to what we write for our sentence. Close enough works. All right, a study recorded the number of beers, same information. Use the least squared regression line to predict the blood alcohol content after 2 cups of beer. And note 1 cup is considered 12 ounces here. All right, so we want our regression analysis. So our BAC predicted will equal our y-intercept, negative 0.0127 plus 0.032, and there's some other decimal places if you want, times the number of beers. All right. And this would be different for wine or other sort of alcoholic liquor drinks and things like that. This is only working for a certain type of beer. All right, now we want to do 2. So we're going to take 2 and we're going to plug it in right there. So we're going to get negative 0.0127 plus 0.032 times 2. And we're just throwing that into our calculator from here. And it's going to give us an answer of 0.051, which would put most of you guys over the legal limit since your legal limit is 0. All right, so there we go. All right, a study recorded the number of beers consumed, blah, blah, blah. Use the least squared regression line to predict the number of beers to be over 0.08, which is the limit in California for someone over the age of 21. All right, so that is a BAC. All right, so we'll set that equal to our equation. Negative 0.0127 plus 0.032 times number of beers. Keep running beers, there we go. Thinking of football from this weekend. So we're going to add this over. So we'll get 0.0927 equals 0.032 times the beers, not the bears, the beers. 0.032 dividing in both of those, just basic algebra 1, solving 2-step equations here. It looks like that's going to be 0.09 divided by 0.03. Looks like that's going to be roughly 3. So 3 beers will put us over the legal limit. All right, so don't go driving. Don't drive and drink. It's just a bad idea. All right, so that's it for regression analysis. So we just looked at a couple of different computer outputs. We just really need to be able to read off the slope, the y-intercept, and the r squared from the model. That's it. All right, so that's it for 4.3. There is no other video for 4.3, so check out the homework for 4.3.